Hello everyone, this is Changhao Chen from University of Oxford. I will introduce my work over the past 4 years on learning methods for robust localization. Localization ability is a fundamental need for human and artificial agents. Self-driving vehicles rely on location information for path planning and decision making. Localization for mobile devices enable many location-based services. The emerging VR/AR devices need motion tracking for better user interaction. Previous researchers have built a variety of model-based localization solutions. However, these hand-designed models might be fragile in the wild. Let me give you a motivating example of the importance of robust localization. We are working on a project to help locate firefighters in emergency response. Statistics show that in the United States, over 2,700 firefighters died on duty over a 10-year period. Sometimes they don't know where they are and how to exit. Huge vision constraints inside a burning building prevent them from saving people and themselves. However, existing localization approaches are hard work in these scenarios. GPS signal is blocked, camera or LiDAR fail due to heavy smoke or dramatic human motion. This motivates us to develop learning methods to achieve accurate and, more importantly, robust localization to overcome the limitations of conventional hand design models. We first consider to learn self-motion from a more robust sensor. Inertial sensor is the ideal choice. It is completely self-contained, not influenced by environmental factors, but it is corrupted with various sensor noise. We formulate inertial tracking as a sequential learning problem and propose IONet, a deep neural network framework that learns self-motion from raw data and recovers global trajectories. Our IONet can work on different people, devices, attachments, and new environment. It solves a more general motion. This video shows trolley tracking experiment with a phone-based MU. This is a difficult problem for classical analytical model. Our IONet is the first approach to solve this. Now we move on to the effective sensor fusion problem for deep learning model, which is underexplored. We propose a generic framework to explicitly model the feature selection process for robust sensor fusion. Our hard fusion is based on Gumbel softmax trick to generate a binary mask that decides whether this feature should be used or not. This framework is employed on a learning-based VIO. This video shows experiment on kitty dataset. Even with the synthetic degradations, our model is more robust and accurate than baselines. It also offers model interpretability. This generic framework can be extended to other tasks like depth vision relocalization and LiDAR vision odometry. Our third question is to solve the domain shift problem for learning-based localization model. Based on generative models, we proposed CDA, a generic sequential domain adaptation framework for long continuous time series data. We employ it on a deep inertial tracking problem. With model trained on one domain, it can still generalize to very different other domains without labeled or paired data. We also work on novel sensors to localization and mapping in challenging environments. Check our update paper if you have interest.